Here's a fun little DSP trick. Given a digital signal, you can actually reimagine it as a line, broken up into segments, where every segment is a sample whose length is based on its relative value to the unsigned integral. For example, here's one sample here. If I increase or decrease it, the length changes, but the length is conserved for normalization. And here's some cool examples: constant, linear, sinusoidal. And what's really cool is that if I take two signals and treat them as the x-axis and the y-axis, I can make a grid. And using this grid, where every cell is a product of two samples, one from each signal, I can then find, say, the convolution, where every sample from the convolution is the sum of the diagonal cells in this grid. And I can also find the cross convolution, which is the diagonals in the opposite direction. And I can also see how if I change any of the samples here, I'm going to change two samples at once. The convolution change, here the cross convolution changes. And what's also cool is that if I were to randomize both x and y signals, then the center of the cross convolution, or the dot product, always peaks. There's also some other cool stuff, like you notice that there are more samples in the cross convolution than in either of the input signals because there are more diagonals than there are rows or columns. And also you notice that the integral of the convolution is the area of the grid, and the area of the grid is a product of the x and y signals integrals. So there's a lot of stuff you can derive from this model. And also, if you had a third axis, you can also create a 3D cube where the 3D convolution would be the finite impulse response, where the third axis would be the kernel of that.